All right, this video is going to be on how to find the antiderivative. So if we look at a function that we know is a derivative, and we said that that function is 8x, then we have a few different answers actually for what the original function could have been. The original function could have been 4x squared, or the original function could have been 4x squared minus 10, or the original function could have been 4x squared plus 14, or the original function could have been 4x squared plus pi. There's a lot of different things that original function could have been, where if you did the rule for the derivative and you multiply the exponent by the coefficient and then drop the exponent by 1, would still get you 8x. So when we find antiderivatives, we're always going to say that the original function that gave us a derivative of 8x would be 4x squared plus c. And that c value could be 0, so that the original function really was just 4x squared. But it could also have been any of these other numbers added on the end or subtracted on the end. So c represents a positive or a negative constant number. Any constant could fit in there. All right, so we're going to say on our notes, so we don't forget, for all antiderivatives, we will add an arbitrary constant. And so that's the c that we put on the end. All right, so here are some of the rules for finding antiderivatives. So here we're going to say if the function is x to the n, where n does not equal -1, and we'll talk more about that later, then the antiderivative is what we would have started with that would have given this to us as a derivative. And so what we do with that is we take the exponent and we add 1 to it, since when we take the derivative we subtract 1, and we would divide that by n plus 1, and then we put plus c on the end. So we did that up here. If we say we've got 8x and that was a 1, so we're going to add a 1 to it and make it 2, and then divide the whole thing by 2. And that's what gave us the 4x squared. All right, and that's going to deal with a lot of our derivatives. And now we want to look at the antiderivative for all the trig functions. So if the function was sine x, then the antiderivative of that is negative cos x. If the function is cos x, then the antiderivative of that is sine x plus c. If the function is secant squared x, then the antiderivative of that is tan x plus c. If the function is secant of x tan x, then the antiderivative of that is secant x plus c. If the function is cos squared x, then the antiderivative of that is negative cotangent x plus c. If the function is cosecant x cotangent x, then the antiderivative of that is negative cosecant x plus c. And if you look at your old notes and you compare what some original functions were, then they would have been these and your derivatives would have been these. So now we're just doing the backwards version of what we spent all of the first quarter doing. So with the notation, we have two different ways of thinking of this. So we can say that we are starting with the derivative. So we have f prime of x, and we are going to the function. Or we can say that we are starting with the function, which we would call f of x, and we are going to the antiderivative, which is capital F of x. So there's two different types of notation for this, and so these are the problems that I gave you to begin with to kind of introduce you to the idea. I said if the derivative is something, then what is the original function that gave you that derivative? And now we might phrase it as, okay, here's the original function, what's the antiderivative for it? So two different ways you might see these problems written. All right, so here are some examples for you. So our first example is we have f of x equals 4 sine of x plus 2x minus root x all divided by x. And what we want to do is we want to find capital F of x. So we want to find the antiderivative. So first, I'm going to fix this because when we do these problems, we are used to whatever this being as a derivative of something that we already found. There's no such thing as a quotient rule. So if you think about it, you used the quotient rule to find your derivative, but your derivative itself was not a quotient rule. So here we cannot leave something as a quotient like that, so I'm going to go ahead and fix this equation. So I have 4 sine x plus 2x over x minus x to the 1/2 over x. So all I did is I took that fraction and I split it into 2 so I could fix it. So the function is 4 sine x. 2x over x, those x's are going to cancel, so I'm going to say plus 2. And then x to the 1/2 over x to the 1. If you guys recall, when you have this, you can just subtract your exponents. So 1/2 minus 1 is negative 1/2. So plus, sorry, that was a minus. Minus x to the negative 1/2. All right, so if we think about all of these to do the antiderivatives, the function I must have taken the derivative of to get sine x would have been cos x. But cos x, if we take the derivative of it, gives us negative sine x. So this must mean that the antiderivative of positive sine x is negative cos x. And if you double check, that's what we had up here. So you don't have to think through it like I just thought through it. That's what helps me remember them. If you want to memorize them this way, that's fine. All right. Plus, sorry, I should be looking over here. The antiderivative of 2 would be 2x minus, and now here I'm going to think of taking my exponent and adding 1 to it, plus 1. And then dividing by that number. So negative 1/2 plus 1 is positive 1/2. And then I have to make sure I put a plus c on the end. So I can go ahead and clean this up. My antiderivative is negative 4 cos x plus 2x minus, and then if I look at this, when I divide by 1/2, I can flip that up. I'm using the reciprocal, so that gives me 2 over 1, or just 2. And then that would be x to the positive 1/2 plus c on the end. And that is my final answer. All right, let's look at some other examples. Here's our next one. We're going to say find f if f prime of x equals x square root x and f evaluated at 1 equals 2. So just like I said before, when we look at this, we could have used a product rule to get our answer for what the derivative was. But as far as using derivatives and going backwards and finding their functions, there is no such thing as the product rule. So that means that we need to rewrite this derivative as x times x to the 1/2. And x, that's x to the 1 times x to the 1/2. We add our exponents when we multiply like that. So 1 plus 1/2 would be 3/2. So this is what we were trying to find the antiderivative of. We want to go backwards and find the function. So my function would have been x to the 3/2 plus 1, so 3/2 plus 1, which is 5/2, and so I'm going to divide by 5/2. Then I got plus c on the end. So our original function is 2/5 x to the 5/2 plus c. Now what we want to do is go back and say the original function evaluated at 1 equals 2. So the original function evaluated at 1 equals 2. And what that's going to do is that's going to allow us to solve for our c value. So 2 equals 1 to the 5/2. 1 to any exponent is still just 1. So 2/5 times 1 is 2/5. And 2, if I subtract the 2/5 over from the 2, that gives me 8/5 equals c. And so that means that in this case, I'm not going to have an arbitrary c for my function. I know what the actual c value is. So that gives me 2/5 x to the 5/2 plus 8/5. And that is my function. And again, I was only able to do write the equation that specifically because they gave us a point to plug in. All right, and then here is our last. We're going to say find the function if the second derivative of the function is sine of x. And they're going to tell us that the derivative evaluated at 0 is 1. And the second derivative evaluated at 0 is 6. Or not the second derivative, sorry. The function evaluated at 0 is 6. Okay. So if we have that the second derivative is sine x, then for the first derivative, I'm going to think, what could I have as my function that would have given me the derivative of sine x? And I know that the derivative of cos is negative sine, and so this must have been negative cos. So it would have been the negative version of negative sine. So negative cos x plus c. And then they gave us a point to use. So I'm going to say, I'm going to plug in 0. And I know that it's going to equal 1 when I do that. So if I consider my unit circle, 0 pi radians, or 0 degrees, is right there on the unit circle. And that point on the unit circle was 1, 0. So cos evaluated at 0 is the x-coordinate. That's 1. So 1 equals negative 1 plus c. And so I can add the 1 over 2 equals c. So that means that my first derivative is really negative cos x plus 2. So now from there I can find the original function. The function that must have given us a derivative that was cos is sine, because the derivative of sine is cos. And if the derivative is negative cos, when you took the derivative of sine, if you remember, the derivative of positive sine gives you positive cos. So that means that we must have started with negative sine to get a derivative of a negative cos. And then the derivative that would have given us a 2 would have been 2x. And then we have to add our plus c on the end. And now is where we can go back and plug that point in. So I know that this function evaluated at 0 equals 6. And if I look over here at what I drew, the unit circle evaluated for sine at 0 is 0. It's the y-coordinate. 2 times 0 is also 0. And so that means that my c value is 6. So the original function must have been negative sine x plus 2x plus 6. All right. Now this last part might seem pretty obvious to you. I just want to go ahead and write it out anyway. So when we were doing physics problems, if we were taking the derivatives, we started with the position function and then we said the first derivative was the velocity function, and the second derivative was the acceleration function. And now, if we are taking antiderivatives, we're going to be moving backwards. So we're going to start with the acceleration function and say that the antiderivative of that is the velocity function, and the antiderivative of that is the position function. So just keep in mind that now we're working our way backwards.